have, starting from the CAD model, we are able to build the material. And this is quite different with respect of the additive, the traditional subtractive, let's say, manufacturing approach, such as milling, turning, and so on, where we are going to reduce the dimension of the initial block for getting the dimension and the shape that we need. And this means also that the characteristic of the material will be quite different with respect of the one. And there are a series of problems that must be considered for when we deal with additive manufacturing. What are the processes? Indeed, I would say that we can distinguish three main categories, families of processes for additive manufacturing. For sure, the most popular one today are the thermal processes that can be both on laser powder bed fusion processes, such as the selective laser melting, or can be also the so-called directly energy deposition, like the WAAM, that is this, where you have a wire that is put in the right position and an electron beam that is melting the material, the wire. And in this way, by melting the powder, we are selectively melting the powder, we are able somehow to get the desired shape and the desired component. Then we can use the chemical processes, generally binder jetting, where indeed we are using a powder bed also in this case, and by means of a binder, we can selectively apply the binder in such a way that we obtain step by step, slide by slide, the desired shape. And in this case, we need also sintering for completing the process. And then the last one, maybe the youngest one, at least as regards the ability to be used as an additive manufacturing process, is the so-called cold spray. Indeed, that is the one, as the chairman said, is the other main research interest today. And in this case, we are not going to melt the powder. We are using kinetic energy to get the addition of the powder against a substrate, the target material. And what is cold spray? We can say that cold spray is a dynamic process where, by means of a preheated and pressurized gas, generally nitrogen, helium is better, but it's much more expensive. So nitrogen is generally used. We can accelerate the flow of powder from a feeder in a de Laval nozzle, a supersonic nozzle, in such a way that we can get a supersonic speed that is beyond the so-called critical speed, that is the minimum speed where we can get addition and not rebounding or erosion of the material, of the substrate material. And this is the other process. And today, indeed, this is today not still completely digitalized. That is, is more used for repairing, it's more used for coating, for getting the complex shape. It's under evolution, under development. But the advantage is that the deposition rate is 10, 15 times larger than the other thermal processes. We can spray more than 15 kilograms per hour, and that is much more than what we can do with SLM or the other processes. Anyway, whatever is the process, indeed, this is the motto of additive manufacturing. Freedom for nothing. Indeed, what does it mean? It means that we can, by a proper design of the part, we can get light part with optimized shape, like in this case, where we have a topologically optimized material part, much lighter than the one that we can get with traditional processes. The same here is the two geometry, the two design concepts are, one is with traditional processes, the other one is optimized and obtained by using additive manufacturing. We see that the second one is much lighter and the use of the material is much better. And here we can see another peculiarity of additive manufacturing, that is the ability to get lattice structure, reticular structure, that for unique properties, and in this case, this is applied to a biomedical prosthesis. And this is a heat exchanger for an experimental exchanger for for a motorcycle that we developed at Polytechnic in cooperation with a company. And in this case, indeed, this is much more, this is a research prototype. This is much more expensive than traditional heat exchange. But in this case, we can also design the material and the shape in such a way to have a much more efficient heat exchange. And so this is another topic that is under development to optimize and to use additive manufacturing for heat exchange, for optimized heat exchange. But indeed, it's really true that freedom is for nothing. Maybe not, because indeed, something we need much more energy. So for some products, this could be convenience, for some other not, in terms of thinking to the environmental sustainability and to the energy consumption. For some products, it's better to have light product by spending more energy initially at the production stage. For some other, maybe not. And anyway, we are not able to get generally the as finished surfaces and as finished part. That what does this mean? That the part that we obtain by using additive manufacturing have not a great quality in terms of internal defect and also in terms of surface quality. This is a cross section taken from one additive manufactured part, and so we need surface post-processing. And indeed, it's surface post-processing is an important part of the technological cycle of additive manufacturing. And I recently read a magazine, an American magazine, where probably it was machine design or mechanical engineering, where they said that the post-processing can contribute for more than 30 up to 40% of the total cost of the production of additive manufacturing parts. So this is indeed, so we have two reasons to investigate this post-processing. One is to improve the quality of the part and the material in such a way that also the mechanical properties are suitable for the application of Intel. And the second one is to reduce the time for post-processing, to optimize the post-processing in such a way that also the cost and the total time for the technological process can be reduced. These are some images taken from a paper we published in the last year. We have three different processes that are considered: SLM, selective laser melting, electron beam melting, and then the laser MIG arc welding. And here we see indeed how the surface is changing by using the different parameters that define, that characterize each single process. But in any case, we see that the quality of the surface is not acceptable for most of the application. If we look at the SLM, and by varying the energy density, we have a different result. No matter what is the energy density, the result is not acceptable. And the same can be said for the other processes. So we need to post-process, and starting from what? We can start from the definition and the assessment of which are the possible parameters that affect the surface quality of the S-build at the AM part. So we have many factors: feedstock material with the material type and the morphology and so on. Also, the surface can be affected by the initial design of the part. So it's important to design for additive manufacturing in such a way that the shape and the way the powder is deposited is able to minimize, or at least to reduce the surface roughness and to reduce the surface defectosity. The AM, the process parameter, the power source, the travel speed, and so on, and the condition of fusion or depofusion for thermal processes, deposition for cold spray, and binding for the binder jetting process. And also in this case, we have different factors that affect the final result. And so, what does it mean? That in the AM process chain, it's important to correctly design the part and the way we are going to build, to manufacture it by a good design and 3D modeling. Then we have to select the right AM process, but for sure we need to post-process this. So not only the surface, but indeed we know that most of the mechanical damage mechanisms start from the surface. So it's of a particular interest to improve the surface properties by means of appropriate post-treatment. And these are the post-treatment that can be used. We define indeed different categories that include material removal or no material removal. The first one include indeed traditional machining, such as polishing, machining, grinding, or tumbling, and so on, or laser-based or chemical processes. The second one are the one that are more interesting. Indeed, we are not subtracting any material. We are just changing the characteristic we are changing the characteristic of the surface. This and can be mechanical treatment or laser-based treatment. And among the first category, deep rolling can be used, bead blasting, shot peening, that is still the most widely used due to its versatility and the ability to be applied to many different complex shapes, maybe not to lattice structure because of some limitation, but in this case, bead blasting can somehow be used. Cavitation peening is also good because we don't have any ball, any waste in the end, but in the end we use water, pulsed water, for getting the final peening result. And then the ultrasonic surface modification that also in this case is based on traditional shot peening, is a modification of traditional shot peening. About laser-based, we have a laser shock peening and the other laser polishing and so on. And then we have coating that are less used, more used for when we have to define some functional surface. What I mean. Indeed, if we are thinking, for instance, to hydroxyapatite coating, we means that we are using probably for getting a better biocompatibility, and so we are using for prosthesis or some other medical part, let's say. And then we can combine the hybrid treatment. We can combine the different treatment to get the optimal result. And then let me introduce, since now I am focusing mainly on shot peening, let me introduce shot peening in the, it's okay? Indeed, just briefly, you know what shot peening is probably. Indeed, we know that shot peening is a treatment that is based on the impact of several shots of small dimension with a small diameter, with an energy that is enough to get plastic deformation of the surface layer of material. In such a way, what do we obtain? We obtain hardening of the material. That is, we are increasing locally the hardness of the material. We are also distorting the grain side, and we can also, by proper parameter, or we can also refine the grain dimension, and then we are modifying the roughness, the surface, and then we are obtaining an important residual stress field that is compressive in the surface layer of material, and this means that it's very good for fatigue strength and for mechanical strength for more in general. And shot peening should not be confused with sandblasting or gate blasting, where the media are not controlled. And indeed, shot peening is defined by, indeed, the result of shot peening, and is defined by some energy, by total amount of energy that is used for plastic deformation. And this is defined by the kinetic energy of the shot flow and by the total time of treatment. And these two concepts are defined also what is called the intensity of shot peening and the coverage of shot peening. And in brief, the intensity is measured by means of the Allman intensity. That is, we use a thin strip of a fixed material, a steel. We pin it just on the side. This is fixed. Then we remove the screw and we measure the final arc height in such a way that and this is the intensity that is related to the energy that is associated to the velocity, the kinetic energy of the shot stream. The coverage is defined as the time that is needed to pin an entire surface. So 100% coverage means that the entire surface has been interested. 200% means that the time we are using is twice the time that is used for 100% coverage. And these two factors are the ones that affect the final result. So, and if we think to use the so-called pneumatic shot pinning, where we are using the compressed air to get the acceleration, the kinetic energy of the shot, we can measure, we can increase the Allman intensity by using higher compression of the air, and we can increase the coverage by means of making larger duration, increasing the time. And by means of a correct balance of coverage and intensity, we can get surface changing of the surface roughness and grain refinement. We can get a good micro-hardness stress, and then the desired residual stress field. And here, indeed, in this graph, we can summarize what shot pinning can do. Here we have the coverage and the Allman intensity on the two axes, horizontal and vertical. And we see that if here we have 100% is the coverage, if the pressure, and so the Allman intensity is low, we can have the so-called traditional shot pinning. This is the green one, is the green area is the area where shot pinning is usually done. But if we increase the time, we can get also not only residual stress, but also the grain refining and macrostructural modification. And so we can get other advantages. And indeed, we can get the same result by increasing the Allman intensity, so the pressure in this case. And we can define two other areas. The yellow one here, where we have severe shot pinning. What does it mean? It means that we are inducing not only residual stress, but also surface microstructural modification. But if we exaggerate, we go in the field of overshot pinning, where we create some damage, and the benefit that we can get by means of shot pinning will be decreased. Okay, and so this is the result that after this part about shot pinning, let me introduce the result we have got so far. Indeed, as I told you when I started the talk, we are dealing with two cases. The first one is the material is the aluminum silicon 10 magnesium alloy. This is our notch sample with indeed severe notch. This means that the KT, the theoretical stress concentration factor, is around 2 in this case. This is the way we have built the sample. So the direction of building is perpendicular to the cross section of the sample. And here, the first thing that we notice is that the surface symmetrically posed with respect to the minimum cross section are not the same. This is due to the different way that the deposition is done in the upward or the downward phase. And then starting from in this condition where we have a lot of porosity, surface damage, and bad quality of the surface, indeed, we have applied different treatment surface. We apply the NEAT treatment, the T6 treatment, and then we apply shot pinning or ultrasonic nanocrystalline surface modification. That is with a nice ball. We are imposing ultrasonic vibration to get indeed the same result of shot pinning. And then the severe vibratory pinning, that is almost the same, but the media is different. We have a series of still shots, and then laser shot pinning, that where we obtain the change of the material, the change of the surface by means of pulsed laser source. And by means, we start indeed, what do we want to obtain? Starting from this situation full of defect, close on the surface or close to the surface with pore, by means of one of these mechanical treatment, we want to achieve compressive residual stresses, improved and increased hardness, and also surface grain refinement, a graded structure. And then by means of, chemical polishing or electrochemical polishing to improve the quality of the surface, to reduce the roughness indeed. And this is briefly the result that we have got in terms of fatigue strength. The stress was fixed at 110 megapascal. And here you see, indeed, it's interesting to see that the failure's cross-section is not the minimum one. And it's in the as-built material. What does it mean? That indeed, due to the quality of the surface, the crack starts not on the minimum section, but in the downward phase. And this is strictly related to the quality of the surface we have achieved by means of this process. But if we consider some treatment or some combination of treatment, that is AB plus shot peening or laser shot peening, or by adding also electrochemical polishing or simply chemical polishing, indeed the defects are removed, and the section, the failure section, is go back to what is expected. That is the minimum one. And this is the strength, the fatigue strength. And we see here that the importance of the final electropolishing treatment. That is to say that we are able, indeed, shot peening is good, the same is laser. We are able to strongly increase the negligible fatigue strength of the as-built material. But indeed, if we also apply electropolishing, we are able to get also even more interesting and a better result. And these are the same concept expressed in the percentage of improvement with respect of the as-built condition. And we see that just the heat treatment is not enough to get a good result. Heat treatment, and also that if we ignore the heat treatment, the first series of samples, indeed the final result is the same. So the heat treatment, the T6 treatment, is not affecting the final result when some mechanical post-processing is applied. And then let me go a bit more in detail on what we call the gradient shot peening. That is a new way to apply shot peening. In this case, so far we have experimented, we have used smooth sample. This is the geometry. The experiment on the notch sample are on course. Indeed, the process is the same, the material is the same. Okay, in this case, we have not a notch, a severe notch, so the surfaces are more similar with respect of the previous case, but anyway, the quality of the surface, the initial quality is bad. And what is gradient shot peening? Indeed, I have already explained this graph, and usually shot peening is done this way. The pressure is defined and applied and maintained constant for the entire duration of the process. So we start from this value of pressure, and it remains the same till the process ends, till the end of the process, so at the expected, at the desired value of the coverage. And in this way, what's happened? We can get we have the result in terms of residual stress, but if we increase too much, or the coverage, or the Almen intensity, or both, indeed we are getting we are going easily in the overshot peening field, and this is not good. So we apply shot peening by changing the pressure, and so we apply gradient. We call it gradient shot peening, and with two different laws. One is starting from an initial pressure, going up till the end of the treatment, and then going up and down. You see the maximum pressure is the same, but then we go down with the same cover, with the same peening duration. And in this case, why we are doing that? Because we think that we are improving the final quality of the surface, reducing the roughness. So we don't need the electropolishing anymore to get good fatigue strength. So we avoid the problem that is related to overshot peening, where the quality of the surface in terms of roughness is quite bad, and we don't need any other treatment. Okay, so this is in number the treatment we applied in terms of pressure and peening duration. This is the sample. This is the batch of the specimen. We are also applying substance the T6 treatment, and these are the laser process, the parameters that I'm not mentioning due to the limited time. These are the parameter of shot pinning. We use conventional shot pinning. This means 100% coverage and Dalman intensity at 14. Then severe shot pinning, over shot pinning, and then ascending severe shot pinning and ascending descending shot pinning. That are the gradient shot pinning treatment we use. And these are the results. AB is as built plus the thermal treatment, where we see that the characteristic configuration of the material is removed. And here we have the same by the image we can take by means of EBSD analysis, where we can notice that the improvement of the microstructure of the material after the heat treatment. These are some other microstructural observation in terms of grain boundary, with and without the treatment, and by applying the different shot pinning treatment, severe shot pinning, over shot pinning, where the damage can be noticed in terms of grain or recrystallization, and then ascending descending shot pinning. And we can see that the result is different with respect of the different shot pinning treatment we use. And so this is also interesting. These are the results in terms of micro hardness and residual stress measurement. Without, so we have the different shot pinning treatment without and with the heat treatment before, the same for residual stresses. And we see that indeed, first of all, that there is a great improvement with respect of the as-built material, and also that the treatment reduce somehow the residual stress field, especially close to the surface, that they are something close to zero, while we have more than -50 in the not heat-treated materials. The porosity measurement, here we appreciate the effect of the shot pinning treatment in terms of porosity, and we see that with ascending descending, we are able to get better results with respect of conventional shot pinning. Over shot pinning is even better, but with other problems, let's say. And this is the depth of the pore closure after the treatment. And we have seen that from this point of view, conventional shot pinning is not able to go so deep, while if we are considering the ascending descending shot pinning or also severe shot pinning, the effect is much more remarkable. And also in this case, the application of heat treatment is not important, at least for this kind of analysis. Surface roughness, and here you can appreciate the effect of gradient shot pinning. The surface roughness is much better with respect of the base material, of the as-built material, and with respect of all of the other treatment, and with respect also, and is comparable or better with respect of conventional shot pinning, but with other advantage, that is grain refinement and the more deep effect of residual stresses and so on. So we are able to match all the quality of the different treatment by means of this, especially by means of the ascending descending shot pinning. And these are the fatigue result, and the trend is confirmed. Here, also this data is done with the same applied stress. We have different 3 samples for each treatment and the average, and we see that by using gradient shot pinning, we have the best result. No matter, in this case, there is also a slight effect of the heat treatment. But anyway, the main advantage is that we are able to avoid a subsequent step in terms of electropolishing for improving the quality of the surface by means of this gradient shot pinning treatment we have defined. And indeed, the treatment is able to shift the crack initiation point. In the as-built material, the crack initiation point is at the surface. Why, if you are using the shot pinning treatment, we see that the crack initiation point is deeper and deeper with respect of the treatment we have used. And also and the heat treatment is not affecting the position. Just a few words to conclude. Indeed, using surface pore processing is needed for getting good mechanical properties and good fatigue strength. Among the applied post-treatment, it seems that the gradient shot peening plus also the treatment is able to get the best improvement and is able to avoid the typical disadvantages, cons of shot peening related to the roughness of the material, and to avoid also overshot peening. And the gradient shot peening is effective to get the best result that are related to the different shot peening projects that are used so far. In terms of no, it's okay. Then what are the further perspective? What the study we are doing? We are completing the study about gradient shot peening, but we need also some more refined method to relate the individual project parameters. So we are using numerical simulation, and also we are developing some model based on artificial intelligence in such a way that we are able to consider a higher amount of data and a higher amount of treatment. And also high temperature, high dynamic load, and harsh environment should be considered. Designing hybrid treatment is good, and a more systematic study in this field can open new combination of surface treatment in such a way that we can improve and optimize the quality of the mechanical properties of additive manufacturing material. Let me thank my team: Sarah, associate professor, 2 assistant professors. These are the present PhD students. Indeed, you see that the team is quite international, with people coming from, let's say, from different countries. And these are recent the supervised visiting PhD student that I supervised indeed after the COVID period. So starting from Denisa, she was the first one, and the last one is Machen Bin from Nanjing University. Thank you for your interest. Thank you for listening to me and for your passion. Question and welcome, but please don't shot pin me, I would say. Thank you.
Thank you very much, Professor Mario Galliani, for your nice presentation. So the session is now open for discussion. Any questions, any comments? I have one question. Do you have any guidelines related to fatigue crack propagation? Because your presentation were more focused on crack initiation, but do you have any?
Not yet. This is another point that we would like to investigate, to concentrate on fatigue propagation after the treatment. And in this case, indeed, what we are thinking to do, but I also ask you to use the so-called KOL samples in such a way. The CT are not good indeed because of the geometry and the fact that we can shot pin the side, but not the notch itself. If we are using the KOL with a larger radius, we are able to shot pin and also the crack initiation point. And from that point, you should be able to also to analyze how the crack propagation is affected by these treatments.
Thank you. Only another question. Do you think these processes are applicable for other types of materials, like, for example, titanium alloys, or they are only valid for aluminum?
No, indeed, the parameter will change, but the treatment and the way they are applied are of interest for all the metallic material. Indeed, shot pinning is widely used from titanium alloys and from steels, and the same for additive manufacturing. This can be done. Indeed, so far, aluminum alloys are the most widely considered for SLM at least, but anyway, we expect that also for other material, other alloys, this is effective. But it's important to study and to change the parameter. And also for this, it's important to develop something larger that is based also on simulation, also on an artificial intelligence model, just to collect more data and training and so on.
Thank you very much.
Thank you.
So let's move on to the next talk. The title is a methodology for the fatigue characterization of parabolic lift Spring in Freight Wagons by Vitor Gomes, José Correia, Gregor Legiuk, and Abilio Jesus. I think it's an online presentation.
Yes, good morning. Can you listen to me?
Yes. Please, Abilio.
Yes, and
Start.
can you see my presentation as well?
Everything works okay?
Okay, thank you. So, dzień dobry. Sorry for not attending in person the conference, but I'm anyway pleased to join you virtually. And today I will talk about a project that we have in the Faculty of Engineering from the University of Porto, from Portugal. And this is a collaborative work of many colleagues, including Professor Gregor Legiuk, that I am also very pleased to know, and I congratulate for this organization as well. So this work that I will present here actually is an overview of a PhD project that is about to finish by my student Vitor Gomes. Vitor Gomes presented you yesterday a small piece of his PhD about critical distances, and today I will give the overview of his PhD work and about the project goals. So this is about railways, about freight wagon maintenance and fatigue prediction. And this is in Portugal. I would say that for a few decades we had a poor attention for the railway sector, but nowadays I am a believer, and I believe that we are starting the betting in the railway sector again. So I believe we are in the renaissance of this transportation sector in Portugal, not only for passengers, but also for freight or goods transportation. So this is a project about the methodology for the fatigue characterization of suspensions of freight wagons. And the talk will be about, so I will make an introduction, a brief one, then I will go directly to the methodology, and after I will present some results in different perspectives of the project, and finally some conclusions. So regarding the introduction, so we are talking of the leaf springs, which are used or applied in freight wagons, those without bogies. So these elements are critical elements because they link the wheel set to the frame of the wagon. So they serve for so they are stiffness elements. And also they provide damping for to absorb the vibrations. So these springs are produced using spring steels that are quench and tempered steels. They rely on residual stresses, let's say compressive residual stresses on the surfaces induced by shot pinning. Very nice to hear Professor Mario in previous presentation. So we are here in this application fans of shot pinning because it gives a very important benefit for fatigue resistance of the springs. Then these springs are optimized. They are, I would say, for a long time, developed at a long time ago, and they are very optimized in terms of geometry. They usually have protective painting to protect against environment agents. So, but why we are studying this? Why we are studying these springs since they were developed for a long time ago, because we still have failures in these springs, and sometimes they are unpredicted failures, and since they are critical elements in the wagon, those failures could lead to major, let's say, economical losses and sometimes human casualties. So that's why we need keep studying these elements and contribute to their maintenance in order to avoid such kind of failures. So this slide shows you very recent pictures of the what I am saying about the fatigue failures in the lift springs. They are localized in some specific locations, usually in the central part where we have the buckle that links to the wheel set. But there we may have some notches. But sometimes cracks could appear in other regions without apparent notches, at least macro notches. So the objective of our work was to provide, let's say, a framework for addressing this problem, and at the end to provide this approach to the industry, to the operators of the infrastructure. So we start with a plan involving in this plan 4 phases. We have in this data acquisition. This is very critical because sometimes the standard approaches for the loading are not appropriated. So we must take care of the current situation of the tracks, of the railways, because sometimes they are not in good shape. So we must be aware of that. So data acquisition from field measurements are very important. So we take care of that in our project. That data we need to make data analysis, data reduction analysis, and we also need to understand how the springs behave globally, and also we need to reach local stresses. So we need to characterize the springs very comprehensively in terms of mechanical behavior, global one, but also under residual stresses, assembling stresses, surface roughness. We need also to characterize the material, take into account fatigue, behavior. I will show you some results. Then we will make the assessment, and the final phase will be the decision about palliative interventions, replacements. So this is basically what we are proposing, and I will show you now some of the results. Regarding the material, this is a very well-known material, not only used for freight wagons, springs, but also for trucks. So this is a spring steel with very high strength. And what I have to say here, we just make some samples from different springs, and we found a very significant scatter in the properties. So that was the first concern that we observed in this material. Also, some inclusions in material were also visible in our analysis. Then we start to more classical characterization of material. We start, even this is spring steel, we can observe some plasticity, some ductility. So we start with some, let's say, we try to cover all fatigue regimes from low cycle to the very high or gigacycle fatigue regimes. So in terms of low cycle, we got the cyclic curves of the material, the strain life equations, we correlated some numerical, some constitutive models for numerical analysis. Then we also got some fatigue crack propagation laws, including the threshold regimes. For the moment, we are not exploring this information, at least we are not using the fracture mechanics based fatigue analysis. Anyway, this information will be useful for, let's say, critical distances analysis in order to define the critical distances. But of course, we could explore later these properties or this behavior also for fracture analysis and fatigue-based fracture analysis. Also, we perform, so in this case, we put our more energy, we put more energy on the fatigue SEN characterization of the material, because we believe in this case crack initiation will be the leading damage mechanism. And for that we cover a lot of different situations, like different loading conditions. So we change mean stress in the tests. We also consider, as you can see here on the right bottom, we cover also gigacycle fatigue regime. So we did some tests still almost, well, 10 power to 9 and almost 10 power to 10 for some cases. So using a gigacycle, so testing systems like piezoelectric ones. And we try to combine all the data together in the SEN, probabilistic SEN field. Then we also look for the notches. We did a lot of tests concerning notch specimens. We applied then the critical distances theory in order to combine all the data in one unique plot. So we drive the probabilistic SEN field for the material. Then in another way, or in a parallel work, we also work in what I used to say, we try to create a digital twin of the spring. So in that way, we test some springs in laboratory to get the very accurate response of the spring, and we calibrate with that information our numerical models. So we are comparing not only the global behavior, the stiffness behavior, but also the local stresses in some hotspots of the leaf springs. Then we also we take care of the assembling stresses. So leaves, when are assembled, we are also introducing some stresses, and that will change the mean stress of the springs. And then we also look for the residual stresses induced by shot pinning at the surface. And this is very important because we can achieve almost 80% of the yield strength of the material under compression, which will change significantly the mean stresses in our springs. After calibrating our numerical model of the spring, so what I call the digital twin being ready, we went to the terrain, to the field, and we did some campaigns, some monitoring of a real stress spectra in our wagon. So we instrumented a wagon with some displacement sensors and strain gauges placed on the leaf springs. And then we monitor some, let's say, in one main track in our country from north Porto to south Sines. We monitor that in that track the sensors during the traveling. With that information, we did some analysis. We got the spectra of the displacements. After the displacements, we were able to get the stresses using our digital twin model and also validate with strain gauges measurements. So we were able to capture satisfactorily the stress spectrum in the springs, and then with our data we were able to get some predictions. So we start with the displacements, and then we got the stresses spectra, and then we were able to apply our resistance data in probabilistic form, covering stress ratio effects, residual stresses, and so on. And we were able to make some preliminary assessments. And for this track, this is the main track in our country. We observed that for these cases, the damage was not significant. But of course, we must make predictions for, let's say, a number of trips larger. So this is just one trip. So that's why the levels of damage are lower. So this is what I have to bring today to you. This is a global methodology, that relies on fatigue resistance characterization of the springs, which in a very, let's say, comprehensive way. Also, instrumentation or in situ measurements with sensors. Our idea for the future will be we are now in a project developing a new wagon, what we call the smart wagon. The idea is to have sensors embedded in the wagon and to have a real-time damage index for the wagon during their operational life. So thank you very much for your for this opportunity and for your attention to this presentation. Thank you.
Thank you, Professor Abilio, for your nice presentation. So we are a little bit late, but we have time for one question. Any questions, any comments from the audience? No. Abilio, I have a curiosity about your numerical model. Is it based on a linear elastic approach or elastic plastic?
Yeah. This is a linear elastic model. As I told, this is
so maybe I think we can move on to the third.
Hello, I think I lost connection.
Yes,
sorry.
Yes.
Yeah, so I was telling that the idea is to develop a digital twin, let's say, of the spring. And in that purpose, we rely on elastic model, which is globally acceptable. Of course, we can run afterwards in some spots some nonlinear models or constitutive equations, but that should be done by post-processing elastic results. Otherwise, this model could not be, let's say, applicable in real time, which is our goal.
Thank you. So the third talk is given by Bartosz Mazurek and Adam Nilsson, and the title is Influence of Power Spectral Density Averaging Fatigue Life Calculation.
Hello, everyone. My name is Bartosz Mazurek. I'm from the University of Technology and Science and Technology Park in Opole. And I want to show the influence of power spectral density averaging on fatigue life calculation. This topic is a part of my PhD studies. And our presentation outline is, of course, introduction. Then I want to show you our adopted research algorithm in this case. And of course, subject, research subject. Then I want to show our PSD simplification, which we applied in calculation and simulation. Then description of the calculation, simulation, and results of the measurement and calculation. Introduction. Regarding to the introduction, in simulation, in FEM simulation, we can make a simulation of fatigue life in fragrancy domain, but we must have a PSD for this, and the PSD which we have measure the acceleration which we measure. Then we made a PSD. We have a large of points, and we have a problem with programs to implement the PSD in simulation. So we decide to make some of simplification of this PSD and check if how it's work in calculation of life damage. So of course the automotive and another in automotive they made the test, but they have a very simple load test profile for the simulation, but we want to check it's okay for the simulation. So the research algorithm is 4-step: the real measurement, the calculation of the PSD, then determining the characteristic load, the model PSD, and we want to make a envelope of the graph, and then we want determining the fatigue damage in selected structural component and made a calculation of the fatigue life. Description of the subject. This is the transport device which we can adopt, but mounted on our car hook and transport the motorcycles. This is the model, the transport device from the Science Technology Park, and we want to check it in real life how it's work, and measure the acceleration on the hook. We made several measurements on the asphalt road, so on the paved and unpaved road. Then we made a PSD and want to check the simplification, several simplification. We made a tool of the simplification of the PSD. We decided to make a local minimum and maximum, and this is the first of the simplification, and the second one is the downsampling method. At the first step, we made a comparison of the area under the graph. The first graph is from the normal P-Welsh. We made the PSD, and the area under graph is 6.8. In a downsample method, the area is larger by 0.8%. And when we have a min and maximum method, we have 22% larger area under the graph. And next step is the simulation. We made it in the in ANSYS. We can implement the PSD acceleration, and we made it. But the first step is the static structural. We test the device and decide which element we can on which element we can do the next simulation in modal and and simulation of the fatigue life. So we've focused on only one element and made the simulation and decide where is the point, the node from where we have the response of the PSD. And the simulation data we take. So we take the PSD from selected node of the element. And of course, due to the small damage, we decide to rescale the PSD response, but it's no impact to the comparison of the results. And the first, we have the distribution of amplitude based on the selected model of the Rayleigh and Dirlich. And life estimation in days, in downsampling and min-max method. It's very similar. So the simplification we made have no large of the deflection or it's very similar. So we can make a simplification of the PSD in this case. So if in future we want to make the same thing, but the same measurements, but in different loads, so different motor cycles on the device, and of course different roads, so different unpaved road, but with different. And then the comparison will be better. Thank you.
Thank you for your presentation. Any questions? Any comments? I have one question about the signal that you have recorded in your real acquisition tests. How long is it? Because in the PowerPoint was not completely clear.
How long is the signal of the? It's about maybe in minutes. It's 1 minute.
Yes.
It's 1 minute of the measurement when we take a road.
Do you think it is representative for
only the unpaved road? Sorry, on the paved road. Yes.
Okay.
So this is the representative because we have the road on Science Technology Park, which is as long as possible. But of course, it's okay in this case.
Yes. Okay. Thank you very much.
Thank you.
Michael.
Oh,
So we have a small change in our session program. The fourth paper is a new one. It will be presented by Mohamed Al-Kazalia, Stanislav Stale, Pavel Pokornik, Gregor Flesch, and Simon Bueller. The title is Comparison of Fatigue Crack Propagation Rates in High-Strength Steel S4060, S6090, and S9060 under stress ratio equal to 0.1. Please.
Thank you for the introduction. Hello, everyone. So my name is Mohamed Al-Kazali. I will be talking about comparison of fatigue crack propagation rates in high-strength steel S460, S690, and S960 under stress ratio of R equal 0.1. I will be representing under the name of Brno University of Technology, Czech Academy of Science, Institute of Physics and Materials, Wrocław University of Science and Technology. So to start off, I will be talking about my main focus, which is the high-strength steel, which gained its popularity due to its outstanding mechanical properties, which will inspire like many works, this work and works to come to get to know the material more and be able to properly utilize it. And the comparison will be done based on two machinery sets. One was done here in this institute, which was the mechanical testing machine, 100 kilonewton, and one was done in Brno and the Institute of Physics of Materials, that Emsler machine. Looking at the material, we can see the chemical composition as what's provided by the manufacturer for all three types of steels. Then some mechanical properties. The tensile test here, we can see the differences in the behavior of each grade of steel. The elongation, of course, the strength with respect to the grade, of course, and similarly to the hardness test. We can see the minimums are in blue, maximums in red, averages and standard deviation in green. We can see some variations between the samples of the same grade here. And worth mentioning, in the experimental setup, it was in compliance with the ASTM E647. And talking about the machines, the Amsler machine have an integrated camera system that monitors and measures some of the specimen aspects like crack length. It's a fatigue specialized machine and it focuses on crack propagation rate. And unlike the MTS machine or mechanical testing machine, which is more versatile and can be used for various testings or mechanical testings. And here is a look at shots from both, one in Brno and one here and at this institute. And looking at the specimen details, compact tension specimen with all details, and the crack propagation analysis, we can see the Paris curve and Paris law, which helps establish a relationship between the stress intensity factor and crack propagation rate or growth rate. Finding the slope, the coefficient of the crack propagation rate, the threshold, as you know, and all that. And finally, looking at our results, we can see that from now on, like all three grades of we have tested, it always follows the same pattern with both sets of machine. The Amsler usually tends to have a steeper slope, while the MTS tends to start earlier, so always on the left. We can see it clearer here in the S690. And again, it will be the same with the S960. And to summarize it all, we can see that both machines were consistent across all types of steels. It always follows the same pattern. So we have to check to see which results are more reliable or more accurate for us. So we have to compare it with some type of standard or established literature, but it's not easy with these high strength steels. It's not easy to find. I've done some with the MTS results. There was some variation between the results, our results and theirs. And next, I will do it with the Amsler results, and we will see where we go from there. And thank you all for listening.
Thank you for your presentation.
Thank you.
Any question? Any comment? So I have a curiosity. I have seen that you use the extensometer connected to the specimen. Did you evaluate crack closure?
Yes, I think we did.
And did you find relevant differences between the two machines?
I'm not sure I've done like much work on that. I will check it. Okay.
Okay. Thank you. So let's move on to the next talk. The title is A Comparative Study on Probabilistic Modeling of Fatigue Strength Curves and Their Use in Fatigue Damage Evaluations of Repeated Connections. And it will be presented by João Silva, António Mourão, Cláudio Horas, José Correia, and Abílio Jesus. I think it's an online presentation.
Yes, hello, good morning.
Hello, please.
I'm going to show my presentation in a video. I hope you like it.
And I'm currently in my first year of PhD. So I'll present you to my first study that I've been working on. This work is entitled A Comparative Study on Probabilistic modeling of fatigue strength curves and they use the fatigue damage evaluations of the connection. This work as a participation from Antonio Mora, Bobby Lawrence, Jose Correa, and Arius Sush.
Sorry, the quality of the sound is very bad.
First, I will briefly introduce the fatigue and the concerns have metallic structures, especially in all metallic bridges. Then I will show you the methodology behind this work and specify the steps that were made by the other authors of the work. Then I will present the corresponding pro-risk analysis performed with various pro-risk models, and after that, the corresponding fatigue damage assessment will be presented, and to conclude, the conclusions and future works will be presented in order to include this. So, as we all know, fatigue is regarded as one of the principal causes of component and structural failure of metallic structures. And by looking at this table, fatigue is a damage caused with the highest number of failure causes in metallic bridges, followed by environmental causes that can also influence the fatigue effect in its structure. Some 200,000 metal bridges have identified reactivities, and in the USA, the number of reported cases is 3 times higher. At the bottom, you can see a graphic of the distribution of active-risk bridge per state in the USA. And the proposal of this work is to show and compare various pro-risk models and how they can predict the fatigue life of metallic bridges, and especially to prove that some standards are too conservative. For that, the old metallic structure in this study will be the Barth Bridge, a bridge located in Portugal that belongs to the Beira Alta line, which connects Portugal to Spain. So, the global methodology used in this work is presented here in order for you to have a better perspective of where my study is dealing. The methodology starts in the step 1, where we get the material information by experimental or bibliographic information. Then we get some bridge information, such as geometric properties, numerical modeling, and building scenarios. And to finish to step 1, we get the elastic material global model, where the fatigue critical detail is identified. And the step 2 enters the dynamic analysis using normative and real traffic scenarios. And once the critical section is defined, we move to the local salt model. In step 3, the Barber rule was used to convert the numerical strength field into elastoplastic structural response. Then, based on local approach, we took the fatigue indicator per meter in order to calculate the fatigue level. The material information was taken from the literature. We have data from the written connection and data from the material. In this case, the data from material is from the S355 modern steel, which has similar performance to the ST52 Barton bridge material. Here you can see the data from single shear interconnection and data from the double shear interconnection, and the normative curves from the American standard and the Euro code. We also can see the SN curve performed by Camille Sudush on the material in this study. Relative to the bridge information, the dimensions were obtained through an in-situ measurement campaign, and the load model considered was a heavy track scenario. Here is an overview of the global model, the critical section, and the corresponding local sum. Here we have the stress history for both connection and around the riveted wall, considering the 4 Euro strengths of the heavy traffic scenario. So, moving to the pro-risk analysis. In this work, we consider 2 types of data. We consider the Barton experimental data, and we are also on the experimental data. We use 2 different approaches to fit the curve. We use the most common in our scientific community, the ordinary square regression, as known as classical linear regression, and we also use the total square regression, as known as orthogonal linear regression. We also use some pro-risk models, such as the ISO standard, using normal distribution and the ISO standard using the label to permit the distribution. You use the Cassini-Fernandez-Cantelli free-parameter label distribution model, and finally the hierarchical-based approach. So, using ordinary experimental data from various double-shape related connections, I present here the result of the lowest model using two different frequency approach, and the corresponding mean curve, and also a curve for availability of 5% and a confidence level of 75%. The results show that the ordinary least squared is more conservative in general compared with the total least square relation, showing a lower slope and a lower detailed catalytic tension. On the right, you can see the label to parameter distribution model, and the results of this progressive model are the same as the ISO when we compare the two different approaches. At the bottom, we have the Bayesian approach for the probability of failure 5, 50, and 95%, and we also have the Cassini-Fernandez-Cantelli model and the balance of these three parameters. So now with more data, in this case I have experimental test data of other double-shape related connections, such as data from the farm ridge, from behind a ridge, both located in Portugal, and data from the Tarzan database. Here we have the curves of the veil and the normal distribution using the two types of regression, and we can see one more time that the ordinary represents itself more conservative, and comparing the two distribution, the veil distribution presents more conservative. Using this time, the Bayesian approach, using the two types of regression, the result shows very similar curves. After all of these probabilistic models, we get the properties necessary to calculate the fatigue life population using the polynomial model, and the results show that the Bayesian approach has the lowest slope and the lowest detailed characteristic, which ultimately results in the lowest damage. We also can see that the material curve provides us with a more conservative perspective compared with the component analysis. We conclude that for both the ISO and the analysis, the least square model results in a more conservative SESJA curve. For the related connection, 34 higher fatigue damage. For the extended related connection database, the total least square once again produced a closer fit to the data, resulting in a lower cumulative damage, and lower damage was found for the critical sections model when compared with the global SESJA analysis. To improve this work, I will add more experimental data at the related and the material scale, including microstructural characterization of the material around the related hull. I will expand the work to other fatigue indicator parameters and accumulation rules, such as the Huffman rule and the sequential law. I will leave a plot of a submodel of the grain lab for the critical location with and without fatigue crack in order to determine the response and the fatigue behavior at set scale, and I will determine the material microstructural defects, such as voids, non-metallic inclusion, and respective distribution in order to regulate its effects on the fatigue behavior. Thank you for your attention. I also want to thank my base funding, and thank you all.
Thank you very much, João. The session is open for questions. Any question, any comment from the audience? No. I have one question about your traffic loading conditions. Did you use real information or data from, for example, Eurocode?
Yeah, the low scenario was the heavy traffic scenario of the Eurocode 3.
Are you planning to use real data?
Okay.
From different loading scenarios, different trains and speeds and this kind of things?
Okay, thank you for the suggestion.
So Let's proceed with the last talk. The title is Probabilistic Modeling of Fatigue in a Structural Component Using a Multi-Scale Material Detail Approach by Carlos Rebelo, Bruno Pedrosa, José Correia, and Gregor Legio. I think it's an online presentation as well.
Yes, good morning. Can I share my screen? Okay. Are you seeing it?
Yes,
Okay.
please, you can start.
Okay. So good morning, everyone. My name is Carlos. The work is entitled Probabilistic Modeling of Fatigue in a Structural Component using a multi-scale material detail approach. So I will follow this structure where I begin with a brief theoretical exposition of the most relevant subjects, followed by metallographic and mechanical characterizations. Next, I'll talk about the global analysis and the respective experimental campaign. I will then present a local approach and finalize with the conclusions resulting. The main objective of this work was to analyze a plate with a central hole made of S235 steel. A global fatigue analysis was conducted and 3 local initiation models were analyzed to see how each one fits the experimental data. This steel has become increasingly important in the field of structural rehabilitation as it is similar to materials previously used and currently discontinued. Since building new infrastructures is costly and time-consuming, this material is being used for maintenance and reinforcement. Moving on to theory, this work focuses on analyzing 3 different local fatigue initiation models. The first, the Coffin-Manson-Baskin model, is probably the best known, relates local deformation to fatigue life. In turn, the SWT model considers the effect of local maximum stress. And finally, the strain energy density Huffman model, possibly the least known, takes into account the effect of strain energy density. The CMB model equation is presented here. The elastic deformation component was proposed by Baskin. The plastic component was proposed separately by Coffin and Manson. And it was moreover proposed the sum of these 2 parts and introduces the effect of the mean stress. The parameters are obtained experimentally by testing the material. Here I present the equation for the SWT model. Although the parameters presented are the same as in the previous model, they take on different values. They are also obtained experimentally. Finally, the damage parameter of the model proposed by Huffman is calculated according to this function. It is equivalent to the CMB model, taking into account the equations presented for the 4 fatigue parameters. This considers the deformation energy of these locations, the critical dislocation density, and the cyclic properties of the material. The models presented make it possible to determine a fatigue curve, which can be approximated to a straight line. However, they will determine a mean curve. Given the dispersion of results, a probabilistic analysis is important to avoid this problem. It consists of translating the curve, the fatigue curve, taking into account the properties of the normal law and establishing a safety margin. In this way, the reliability of structural elements can be guaranteed. So the translation of the curve is obtained according to this equation. The translation depends on the subtraction of this last part, which considers the standard deviation, the sample size, and the tolerance limit for a normal distribution. So this concludes the theoretical exposition, and I now move on to metallographic characterization. It consisted of grain size, microstructure, and X-ray diffraction analysis. For this purpose, small samples of the material were prepared and subjected to the process described here. Initially, the sample was wrapped in resin to make it easier to handle. This was followed by the removal of the oxidation layer using water sandpaper on a turntable. Diamond paste was applied to remove the striations caused by the sandpaper, And finally, to make the grain boundaries visible, the sample was attacked with nitol, a mixture of nitric acid and alcohol. Once the samples had been prepared, it was possible to take microscopic images of the material. These were obtained using a scanning electron microscope, and it made possible to determine the grain size of the material. It was calculated using the intersection method proposed by a STM standard. The ImageJ program was used to draw the lines and establish the scale of the image, with a picture on the left as an example. And an ASTM G equal to 9.64 grain size was determined. The image here on the right shows perlite corresponding to the darker areas and ferrite corresponding to the lighter areas. The presence of perlite are likely influences the material strength, with higher abundance leading to increased strength. An X-ray diffraction analysis was carried out. A Cooper beam was used, and the data obtained were adjusted in the Origin Pro software, resulting in the diffractogram presented here. 5 diffraction peaks resulted, and the respective Miller indices are shown at the top of each one. The table of results is shown here. The first 2 columns corresponding to the angle of incidence and the width at alpha of the peak are taken directly from the X-ray diffraction analysis. This makes it possible to determine all the other parameters presented here. The most important of these are the dislocation density and the Burker's vector, which are necessary to apply the Huffman model. I will now start the mechanical characterization. This part is divided into 2 sections, initiation and propagation. The initiation component was characterized based on the results obtained by Carvalho. The tests were conducted in accordance with the ASTM standard under strain control and the stress ratio of -1. The specimen geometries are shown here, and the hysteresis loops are represented in this graph. The values of stress amplitude and maximum stress, percentage of plastic and elastic deformation, and of course, the number of cycles until failure were obtained. With this data, it was possible to determine the cyclic curve of the material. It is described by the Ramberg-Osgood curve presented here. The coefficients n and k correspond to the exponent and coefficient of cyclic hardening, respectively. By considering only the plastic component of the equation, it was possible to determine these parameters through linear regression on a bilogarithmic scale. Curves at 5 and 95% were determined. The values obtained are presented in this table. The DNV standard values are also provided. The graph illustrates the 4 cyclic curves obtained with these values. It was observed that the DNV curve lies below all the other curves, making it more conservative. The 95% curve allows for the determination of a more conservative characteristic fatigue curve because higher stress values decrease fatigue life. Following the same method, it was possible to determine the parameters of the CMB model. 2 graphs were constructed for this purpose, one for the elastic and another for the plastic component. And the 5% curve were also determined. I present here the values obtained for the parameters of the CMB model. In the same table, I present the values proposed by DNV. The graph on the right displays the 3 curves obtained based on these values. The curve proposed by DNV provides a good approximation for a number below 10 to the 5th power reversals. However, for a number higher than this, it is a quite conservative curve. A procedure similar to that of the CMB model was carried out for the SWT model. However, in this case, it was necessary to first adjust the elastic component, since the plastic component involves elastic parameters. Also in this case, the 5% characteristic curve was determined. Here I present the table with the values of the mean and characteristic parameters. Once again, on the right, I display the fatigue curve of the model. In order to determine the curve of the Huffman model, it is necessary to know the value of the critical dislocation density. However, it is not possible to determine this value using X-ray diffraction analysis. Therefore, 3 curves were determined, considering the minimum, average, and maximum dislocation density value, and the respective mean square error was calculated. The curve with the lowest MSE was the one with the maximum dislocation density, and starting from this curve, an iterative process was used to determine the lowest MSE, thus arriving at an optimized value for the critical dislocation density. It can be seen that the optimized curve practically coincides with the curve obtained with the maximum dislocation density. Knowing the value of the critical dislocation density, the Burger's vector, and the cyclic properties of the material, it is possible to determine the values of the fatigue parameters, shown in this table. With regard to the propagation phase, 2 tests were carried out in accordance with the STM standard to characterize the material during this period. The tests were carried out in fracture mode 1, applying a constant force, and for stress ratios of 0.05 and 0.25. Here I present the geometry of the specimen and the testing machine. The graph shown here illustrates the experimental points. Considering a bilogarithmic scale, a linear regression was fitted. The regression is given by Parry's law according to the equation presented here. C and M correspond to material constants obtained by fitting the linear regression to the data. This graph shows the experimental data obtained and the data obtained by Carvalho for a stress ratio of 0.01. The mean curve was determined for the 3 tests and characteristic curve was determined. However, there were points below the determined characteristic curve. The BS standard states that the characteristic curve for propagation should be calculated taking into account twice the standard deviation. With this method, there was a significant reduction in points below the characteristic curve. The table summarizes the data obtained. I will now talk about the experimental campaign in the structural detail. As already mentioned, this is a plate with a central hole with a geometry presented here. The tests were carried out with a stress ratio of 0.1. Before showing the results, I'll just make a brief note about the Eurocode. The standard proposes fatigue curves for a 0 stress ratio, and the tests were carried out on this experimental campaign, were for a stress ratio higher than 0. So they would have to be corrected in order to be compared with the Eurocode curve. Taras and Brainer proposed a method for correcting the stress ratio values. For cases where the stress ratio is higher than 0, the correction factor is calculated by this equation. The stress values is then divided by the correction factor, thus determining the stress value for a 0 stress ratio. The normalized stress values are presented here in the second column of this table. It is then possible to compare the Eurocode curve with experimental results. We consider the category of detail 11, which determines the values presented here. The graph shows the mean and characteristic curves at 5% of the experimental results and the standard curve. The Eurocode curve has a very different slope to the experimental curve and is unsafe for higher stress levels. This may be to the fact that the standard does not take into account the type of material. Now, entering the penultimate topic, I will discuss the local fatigue analysis. I'll start with the model used in Abacus for the initiation period. The values considered for the elastic properties are presented here. As for the plastic properties, they were defined according to the stabilized cyclic curve. In defining the geometry, I made use of the double symmetry of the specimen, drawing only a quarter of it. I constrained movements here in I direction, here in X direction, and I applied the stress here at top of the model. A mesh convergency study was conducted. The model was simulated for a specific applied stress value, and the mesh was refined until a variation of less than 0.1% in the results was observed. Taking this into account, the mesh with these dimensions was selected. The largest finite element are here in this area, and the smallest here in this area, where the highest stress concentration is observed. After obtaining the results from Abacus, it was necessary to apply the three initiation models already presented, resulting in these three curves. However, at this stage, it is still not possible to draw conclusions since the propagation component is missing. In the case of the propagation model in Abacus, a purely elastic model was considered. It was not possible to use horizontal symmetry since the crack occurs along that line. The boundary conditions and applied load are identical to the initiation model. A crack was defined here, and the tip of the crack, a circular mesh with 10 counters, was defined, allowing for the extraction of a stabilized stress intensity factor. The simulation was conducted for various crack lengths in order to determine the evolution of the stress intensity factor. The right graph displays the propagation curves obtained through integration on the Paris law. Finally, the initiation and propagation curves were summed, resulting in total fatigue curve for the detail. The graph presents the three obtained curves where the initiation period calculation methods differ. To access the quality of local approach, the MSE of each curve was calculated in relation to experimental results. The Huffman model was the model that best fit experimental data, presenting the lowest MSE. The CMB model presented the second lowest value for the MSE. However, it is an optimistic curve. The SWT model, despite being further away, presents a more conservative curve, which could be an interesting point. This graph shows the characteristic curves of the CMB and SWT models and the Eurocode curve. As I said, the Eurocode curve does not fit experimental results. On the other hand, the characteristic curves present a better fit to the results, since the slopes is adequate and establish a safety margin that includes all experimental points. Before concluding the presentation, I just want to thank FCT and Agenda Nexus for the funding. Now I'm finishing the presentation, and thank you all for your attention.
Thank you, Carlos. So the session is open for questions and comments. No, I have one question. How did you define the crack length to separate crack initiation to crack propagation?
I didn't understand the question.
My question is in relation to your approach. You are dealing with crack initiation and crack propagation.
Yes.
And the question is, for example, in your numerical model,
Yes.
How did you define the crack length?
I use various crack
propagation. The initial crack length, if you prefer.
Okay. I use various crack lengths to define, as the points represent the crack lengths I used. I think, is that the question? No?
Yes, but the initial value for your model, how did you find this length in practice? Because it's important to separate fatigue crack initiation live from fatigue crack propagation. But this is only a curiosity. If you don't know, there is no problem.
I think I'm not understanding the question.
Okay. Thank you very much for your presentation.
Okay.
So the session is closed. I would like to thank again to all of you, in special to the speakers, and I would like to thank Professor Lesjuk for this kind invitation to share this section. So now we have a coffee break. See you around. It was a pleasure to be here today. Thank you.